Hello and welcome to the AICE Chemistry lecture series. In this video, we're going to look at chapter 13.2, which is going to look at both ammonia and ammonium compounds. These are the main family of compounds created from nitrogen that are very popular in the industry that fit a lot of different roles. So let's get started. So first, let's look at the structure of ammonia and ammonium and how they're made. Ammonia is a very important nitrogen compound. It's simply just a nitrogen with three hydrogens bonded to it and a lone pair of the electrons on the nitrogen. Because it has three bonds and a lone pair, ammonia molecules are trigonal pyramidal in shape, or trigonal pyramid, because a lone pair of electrons is going to repel these hydrogens a lot more than they repel each other. It's very common in industry. It is a very common chemical in everything from household cleaning products to chemical reactions in industry to create other chemicals. Its dot and cross structure looks like this, where all of the nitrogen-hydrogen bonds are just regular covalent bonds with one electron from each element, and the lone pair comes from the nitrogen itself. Now, ammonia is the only common alkaline gas, and because of that, it turns red litmus paper blue. And we've seen this. We already talked about this in chapter 12, where a common test for ammonia gas is to use a damp piece of litmus paper, of red litmus paper, and if that red litmus paper turns blue, it's a positive test for ammonia gas. And that can be an indication of a few different chemical reactions when ammonia is created. Now, when ammonia is created, or when ammonia exists, it exists as a base, and that's why it's an alkaline gas. Remember, alkalines are water-soluble bases. So let's write that here so we remember it. Alkaline means water-soluble base. So because they're water-soluble bases, that's going to happen because of this lone pair of electrons. Ammonia, apart from being a trigonal pyramid molecule, it's also polar. The partial negative charge is on the nitrogen with that lone pair, whereas the hydrogens are all partially positive. Because of this, ammonia can attract hydrogen ions and bond to them, making it a base. Because it's an electron, a proton acceptor. When ammonia does that, when ammonia creates a dative covalent bond to hydrogen by using its lone pair of electrons, it creates what is known as the ammonium ion. So ammonium is an NH4 plus ion, whereas ammonia is NH3, the molecule, which is neutral. That creation of the dative covalent bond to hydrogen, creating the ammonium ion, makes ammonia a base, and because of that, that means that ammonium is its conjugate acid. So ammonia base, making ammonium ions a conjugate acid. And because ammonia is not just a base, it is a weak base, that means that the conjugate acid ammonium is a weak acid. Because remember, the conjugate of a weak base is going to be a weak acid. So ammonia and ammonium have this really weird or really useful relationship where ammonia can be used to create ammonium compounds anytime it reacts with acids, but then ammonium compounds can be used as acids, and when they react and give up the hydrogen, they go back to being ammonia. So we can have these equilibriums between the two. And we're going to look at both ammonia as a compound and its reactions, and we'll look at ammonium and its reactions and its uses. So let's keep going with that. But before we look at the reactions of ammonia, let's remember how we make ammonia. Now, I say remember how we make ammonia because we've actually talked about this process before. We talked about the process of creating ammonia actually twice. Once with thermodynamics, where we're studying enthalpy, and once later on when we're studying equilibrium. Ammonia is created in industry through what we call the Haber process. And the actual process is actually very simple. It's the reaction between nitrogen gas and hydrogen gas to create NH3 or ammonia. Because nitrogen and hydrogen are available freely in the air, this is actually a fairly cheap process when it comes to the reactants, because they can essentially be extracted from the air. But the process itself has some intricacies, mainly due to its equilibrium nature. The Haber process, this reaction, is a reversible reaction. It does have an equilibrium, with the forward reaction of creating the ammonia being exothermic. It has a delta H of around negative 92.28 kilojoules per mole. Because of this, how, like we discussed back in the equilibrium chapter, there's a few things that we got to take into consideration when making ammonia in industry. So let's review those, because they will come up. I know we talked about them already with the equilibrium chapter, but it's always good to start reviewing, especially as we're getting closer to the AICE Chemistry exam. Because this is a negative delta H, or an exothermic, so let's try that here. It's an exothermic reaction. Because it's an exothermic reaction, then lowering the temperature of this reaction will increase the yield of ammonia, as it says here. But we have a problem with that, because by lowering the temperature, not only are we pushing this equilibrium to the right to make more ammonia according to Le Chatelier's principle, but we're also slowing down the reaction rate. And that's not something we want. So in industry, we reach a consensus or a middle ground. The reactions usually carry around 450 degrees Celsius, and it's because this is a compromise between the yield and the rate. It is low enough compared to other industrial processes that it still pushes the equilibrium to the right somewhat, but it's high enough of a temperature that the rate of the reaction is sped up and it doesn't get lowered too much. So that's the first point, the temperature. It's high enough that the rate of the reaction is still fairly quick, but low enough that the equilibrium is pushed farther to the right, since it's an exothermic reaction. Pressure is around 200 atm of pressure. And again, that's because high pressure is going to favor the side, according to Le Chatelier's principle, with the fewer moles of the gas. And in this case, that would be the ammonia side. The side with ammonia, the product side in the way that we wrote this, only has 2 moles of gas, which are the 2 moles of ammonia. But the reactant side has 3 moles of hydrogen and 1 mole of nitrogen, making the reactants have 4 moles of gas. Remember that high pressures are going to benefit the size of the reaction with a lower number of moles of gas. So making the pressure high would push the reaction towards the right, towards ammonia. That being said, though, high pressures are expensive. They are going to be expensive both due to the creation of the high pressure, the machinery that's needed, and because of the amount of safety and special tubing that you need for that kind of pressure. And so 200 atms of pressure are a cheap enough pressure that still pushes the equilibrium very far to the right. Finally is the catalyst. The Haber process does have a catalyst that we can use. Solid iron, Fe solid, not ions of iron, but the solid iron, the elemental iron, is used to speed up both the forward and reverse reaction. Remember that in a equilibrium reaction, the catalyst speeds up both reactions, forward and reversed. So this doesn't mean that you're going to get more NH3. It just means that the equilibrium will be reached faster, and so the yield of NH3 will be reached faster. But the yield won't change. It's still the same amount. So these are the considerations and the compromises that the Haber process carried out under, which is, again, the Haber process is the industrial process for the creation of ammonia. So what can ammonia do? Well, ammonia, like we said earlier, acts like a weak base. It is a proton acceptor. And because it's a proton acceptor, it's going to use its lone pair of electrons to pick up hydrogens. Now, whenever these hydrogens are picked up, again, we saw it being done with H+, but they can also be picked up from water itself. When ammonia reacts with water, ammonia acts like a weak base. So I'll put that here, weak base. Whereas water, because it's been paired up with a base, and remember water is amphoteric, is going to act like a weak acid. In that step, in that moment, what happens is that the ammonia uses its lone pair of electrons to pick up the hydrogen, like we see here. Ammonia is lone pair to pick up hydrogen. The hydrogen-oxygen bond breaks, and the electrons go to the oxygen. That creates two things. It creates the NH4 plus ion, the ammonium ion we were discussing earlier, the NH4 plus because you have 4 bonds on nitrogen, which only wants 3 bonds. And so it creates the conjugate acid of ammonia. That acid being a weak acid because it's a conjugate of a weak base. And then hydrogen, or sorry, not hydrogen, but water, losing a hydrogen, creates hydroxide ions. Hydroxide ions are the conjugate base of water, making them a weak base. That's, I don't know, that's kind of can be debated whether hydroxide is a weak base or a strong base, but we can leave that for another time. But this is the conjugate base of water, because the water was a weak acid, and then H4 plus the weak acid, conjugate acid of ammonia. So it's a hydrogen transfer, it's a proton transfer that happens here. The ammonia is going to pick up the hydrogens, making that a base, and the water gives up the hydrogen, or donates the hydrogen, making it an acid. Since ammonia is a weak base, the equilibrium lies very far to the left. Meaning that this equilibrium actually has a lot more ammonia in the mixture than it does ammonium or hydroxide ions. That's why ammonia is a weak base and not a strong base. So that's what ammonia reacting as a base in water looks like. And we've discussed this before again in the equilibrium chapter. But now that we know how ammonia reacts and how it's created, and how it can react with either water or H+ to create ammonium, let's see how this can be used in industry. Because ammonium salts of ammonium, again, ammonium being NH4+, it can create different ionic compounds. So ammonium being NH4+. An ammonium salt, in that case, will be NH4X. Whereas X is some anion that pairs up with this ammonium in order to create an ionic compound. Let me put this a little closer. I put too much space there. NH4X. Right, and then you might have more than one X ammonium, depending on what X is. But ammonia itself can react with acids to create ammonium salts in an acid-base reaction. Because like we said, ammonia, and let me go back to that real quick. Ammonia can react with acids to pick up a hydrogen ion from those acids, creating the ammonium ion. So what happens whenever ammonia reacts with an acid is that it's going to create the ammonium ion, which will then pair up with the anion from the acid. So for example, let's see. Let's make this red. So, for example, here, when ammonia reacts with nitric acid, the ammonium that results from the reaction pairs up with a nitrate ion, creating ammonium nitrate. If ammonia reacts with hydrochloric acid, the ammonium that's created pairs up with a chloride ion from the hydrochloric acid, creating ammonium chloride. If ammonia reacts with sulfuric acid, the sulfate ion from the sulfuric acid pairs up with the ammonium, creating ammonium sulfate. Now here, in this case, we have NH4 2, Because again, the ammonium ion has a +1 charge. Since sulfate has a -2 charge, we need two ammoniums to cancel it out. And finally, if ammonia reacts with the next phosphoric acid, that phosphate ion is going to pair up with the ammonium that's created in 1:3 ratio to create ammonium phosphate. So this is how salts of ammonium are created from the reactions of ammonia with different acids, either nitric, hydrochloric, sulfuric, and phosphoric being the most common examples. So when you do these reactions, just remember, ammonia reacting with any acid is going to create ammonium, and then you're just going to pair up that ammonium with whatever anion the acid had, making sure you keep into account the charges of the anion to put the right number of ammonium there. Now, why is this done in industry? Because this is done a lot in industry. This is done a lot in industry because these ammonium salts are actually great fertilizers in farming. These are the most common fertilizers that we see used in industrial farming, when you see those big machineries and those big giant farms. And that's due for two reasons. Any ammonium salt is soluble in water. Ammonium, the ion, is extremely soluble. So any salt of ammonium has a high water solubility. This is great for fertilizers because you want your fertilizer to dissolve in the water and to go into the plant. So this ammonium salt having high solubility because the ammonium ion is very soluble is a very big pro. The other thing that makes them really good fertilizers is that these compounds are high in nitrogen because of the ammonium and the nitrate in the case of ammonium nitrate, phosphorus in the case of ammonium phosphate, and sulfur in the case of ammonium sulfate. These are all elements that are really, really useful to plants and really every living organism, but mainly to plants, to create things like proteins and DNA and all these other biological structures. So that makes these extremely good fertilizers. Things like ammonium nitrate are going to be used as fertilizers, but also to make explosives in industry. So they're made a lot. Ammonium chlorides are used as fertilizers for some specialty and very specific crops that need the chlorine. They're used for flux. They're used in cough medicine, in batteries. It has a lot of different uses. Ammonium sulfate, again, is used in fertilizers because of its high nitrogen and sulfur content, but also in water treatment. And ammonium phosphate, again, very useful for fertilizers because of the nitrogen and the phosphorus, but it's also used as a flame retardant in different pieces of building material like drywall, as well as different for coatings in different things. So that's the gist of ammonium salts. This is how we make them. You simply just react ammonia with an acid to make the ammonium salt, and they have a plethora of uses, but mainly fertilizers. And again, why? Because high water solubility, high levels of nitrogen, phosphorus, and sulfur, depending on which one you're talking about. All right. Let's look at the last reaction we're going to look at for this section. This the displacement reaction of ammonium salts. So we just talked about ammonium salts and how we make them, what they're used for. But ammonium salts can also have their own reactions. Ammonium salts, when heated with a strong base, so remember, what are our strong bases from way back earlier in the year? Our strong bases are hydroxides, anything with OH minus, of group 1 or heavy group 2. And now we know why, right? We now know that it's only heavy group 2 because as we go down group 2, the hydroxide solubility goes up, so they're more soluble. So things like sodium hydroxide, calcium hydroxide, potassium hydroxide, those are going to be our strong bases. If we heat up an ammonium salt, any of the ones that we just talked about, with a strong base, what happens is what we call a displacement reaction, where the ammonia gas will be displaced and essentially freed, water's created, and then the salt of the, let me do this in a different color, the salt of the cation from the base with the anion from the ammonium salt. So calcium and chlorine will form the calcium chloride. Water is always created. Ammonia is always created. So this right here is the only thing that will vary in these reactions. And the cation comes from the base, whereas the anion comes from the ammonium salt. So this reaction creates a few things, but one of the main results or products of this is that ammonia. Why? Because ammonia is released, we can use this reaction as a test for ammonium salts. If we mix an unknown compound with a strong base and then we heat it, so something like this diagram right here, we can mix an unknown compound, let's say the unknown compound is ammonium chloride, with a strong base like calcium hydroxide. If we heat this up and it turns red litmus paper that is damp, that is being wet, blue, then we know that that unknown was ammonium, some kind of ammonium salt. This is a test for ammonium ions. And again, because ammonium ions are acidic, they will react with a base in a displacement reaction. It's a type of acid-base reaction, but a displacement reaction. And they will release ammonia. So it's going to be a chemical test for the ammonium ion where it will turn red litmus paper blue because it creates ammonia gas. So this setup test for that, right? We have a test tube with the mixture of the, in this case, ammonium chloride and calcium hydroxide, but it could be any strong base. And usually we do this with an unknown. The gas, if it's created, ammonia gas is created, it goes through calcium oxide to dry it, meaning the calcium oxide is going to absorb any water vapor that's created, because we do make water here. And then if we use an inverted test tube, we can test for the presence of the ammonia gas. If that red litmus paper turns blue, then that is a check for ammonium ions in your unknown. But this, again, this can be done with any combination. So let's do a different one. So let's say we have ammonium sulfate, NH4, 2SO4. Ammonium sulfate is still an ammonium salt. If we reacted that with something like sodium hydroxide, for example, NaOH, we will still get this reaction because sodium hydroxide is a strong base and ammonium sulfate is an ammonia salt. The results here, that salt, that ionic compound that's created, is going to come from the cation of the acid and the anion of the ammonium salt. Since sodium is Na+, actually let me do this somewhere else. Since sodium is Na+, and then the sulfate is SO4 2-, then the salt that is created, if we cross this like we're there in honors chemistry, will be Na2SO4. So that's our salt here that's created, our ionic compound. Water is always going to be created. And ammonia, and this is an L, it's my really weird L. And then ammonia is going to be created, NH3 gas. All you have left to do is balance this out, right? So we have 2 sodiums here, 1 sulfate. We have 2 waters that are created and 2 ammonia. And that's going to be our reaction. Notice, very similar, very parallel. Water is created, ammonia is created. Calcium chloride is replaced by sodium sulfate because we're using different ammonium salt on a different base. So we cation of the base with the anion from the ammonium salt, give you that ionic compound. And then once you have all of that, you just balance this out. It just ended up having a very similar balancing to the prior one, but with the base having a different coefficient. And that's it. This is a test for ammonium ions, very common, and that you should remember because you will maybe use it in your paper 3, in your qualitative analysis lab. And that's it for section 2. I will see you all in the next video to look at section 3 and the environmental impacts of the nitrogen oxides.